Hey everyone, Kamusta ka? Welcome to the Electronics Lab. In this video, what we're going to do is look at this circuit and analyze it so that we can figure out the voltage across and the current through and the power dissipated by all of the resistors in the circuit. And we're going to look at a systematic method to do this that you can apply to any circuit that has a sets of series and parallel resistors in it. So let's get started. So the basic process is going to be to reduce the circuit down until it is just one equivalent resistor, and then build it back up, calculating the currents through and voltages across the different elements that are in the circuit. So the very first thing that we want to do is identify some elements that are in series or in parallel. And I can see two blocks that I can look at. I can look at R1 parallel to R2 as well as R3 parallel to R4. So let's just start with the R1 parallel to R2. So we've got R1 parallel to R2 is the inverse of 1 over 400 plus 1 over 100. And that works out to 80 ohms. Okay, so we've got that thing. We've got this set of resistors here, R1 and R2. The equivalent resistance of those two in parallel is 80 ohms. And now let's put that in place of the R1 and R2. And what I'm going to do is I've got a table here that I'm keeping track of the resistors, of all the resistors, as well as the voltages across, current through, and the power dissipated by them. So every time that I do one of these reductions, I am going to add that to the table. So I've got R1 parallel to R2, and that one's 80 ohms. Okay, next I've got R3 and R4 in parallel with one another. So R3 in parallel to R4 is 225 ohms. I can replace R3, R4 with that single equivalent resistance. And I'll add that combination here to my table. So I need to repeat this process of looking for combinations of series and parallel resistors until I've reduced it down to only one resistor. And it looks like I have only one step left. I've got the 80 ohm resistor in series with the 225 ohm resistor. It's not in parallel, it's in series. So it's simply going to be the sum of those two resistances, so 305 ohms. And I have now reduced the circuit down to a single, I'm going to use blue, to a single equivalent resistance of 305 ohms. I'm going to call that RT, total resistance. Now that I've got my circuit reduced down to a single resistance, now I can start building it back up again so that I can figure out what the voltages across and currents through all the different elements are. So now that I've got it at one resistance, I can figure out what is that total current that's coming out of the source. That's going to be in this column. The total voltage is the 12 volts from the source. And the total current will be that 12 volts over the total equivalent resistance of 305 ohms. That works out to 39.34 milliamps. So I can add this to the table here, 39.34. And actually I said amps over here, but I'm actually going to do these numbers as milliamps because all the currents are under an amp. That should have been 39.34 milliamps. Okay, now I can go back a step and replace this 305. And so now I'm building the circuit back up again. Replace this 305 ohm resistor with the R3 parallel to R4 resistance and the R1 parallel to R2 resistance. Forgot to put that one in the table. So the current through those two equivalent resistances is going to be the same as the current that's coming from the source because those two resistors are just in series. So those resistors have that 39.34 milliamps going through them. Now that I know the current through those equivalent resistances, and I know their resistances, I can now calculate the voltage. So if I have 39.34 milliamps going through an 80 ohm resistor, that gives me 3.14 volts. And I can calculate the voltage across the R3, R4 the same way with that 39.34 milliamps going through a 225 ohm resistor. And that gives me 8.85 volts across it. Okay, and now I've got the voltage across and the current through these resistances here, those equivalent resistances. Now I can go the next step and replace the parallel combination of R1 and R2 with the two individuals, R1 and R2. Across those resistances is this 3.14 ohms, volts. So since I know the voltage across these resistors and I know their resistances, now I can calculate their currents. And so that current through R1 will be the voltage across it divided by its resistance. So that's 0.0079 amps, which is 7.9 milliamps. Current through R2, calculate it the same way. Voltage across it divided by its resistance gives me 0.0314 amps or 31.4 milliamps. Now I can replace this R3 parallel to R4 resistance with its equivalence, or that was the equivalence, with its actual resistors. 900 ohms and 300 ohms, and I know the voltage across it. It is this 8.85 volts. So if I know the voltage across the resistances and I know the resistor values, I can calculate the currents. 0.0098 amps or 9.8 milliamps. I also do know the voltages already. I just used that there, that 8.85. And the last current to calculate here is the current through R4. So it'll again be that 8.85 volts over 300 ohms this time. 0.0295 amps or 29.5 milliamps. And the last calculation to do is the power dissipated by each one of those resistors. And since I know the voltage across and the current through each one of those resistors, I can just use the P equals VI equation and do voltage times current, voltage times current, voltage times current, voltage times current to get all my powers. So there's the powers in watts for each one of those resistors. I don't actually need these columns anymore. They were just kind of temporary holders of values as I tore down and then built up the circuit again. But I could use this one. This is the total. So I've got a total voltage of 12 volts, 39.34 milliamps coming out of it. That voltage source sees a total equivalent resistance of 305 ohms. I can now use the power equation there to calculate the voltage or to calculate the power that's delivered by the power source. So that'll be 12 volts times 39.34 milliamps, which is 0.472 watts. And now I've got the voltage across, the current through each one of the resistors. I also know the power dissipated by each one of those resistors. I know the total current delivered by that 12 volt source, as well as the power delivered by that 12 volt source. I'm finished the question, but there's a couple of things I can do just to check my work. I can do a KCL check. So that KCL check would be, does the current through R1 plus the current through R2 add up to the total current? So I've got 7.9 plus 31.4. Works out to 0.0393 amps, which is basically with rounding error the same as what's coming from the source. I could also check R3 plus R4, and that's also 0.0393 amps, which again checks with the 39.34 milliamps coming from the source. I could also do a power check. Does the power dissipated by resistor 1 plus the power dissipated by resistor 2 plus the power dissipated by resistor 3 plus the power dissipated by resistor 4 equal the total power delivered by the source? Power from the source has to be used up by all of those resistors, otherwise the powers don't balance. So if I add up those powers, this number plus this number plus this number plus this number, does it equal the total power? And again, with some rounding, I get 0.471 watts, which is basically close enough to that total power delivered. So the power checks out as well. I could also have done a KVL check. 3.14, does 8.85 plus 3.14, that equals 11.99. So that's close enough to the 12 volts delivered by the source, because there's going to be some rounding as I'm not carrying all of the significant figures through in my calculator. Or I'm carrying the significant figures through, but I'm not carrying all the digits through. So there's going to be some rounding error there. And the bottom line is that you can apply this analysis process to any circuit where you've got a single source and a combination of parallel and series resistors. Break the circuit down till it's just one resistive element, one equivalent resistive element, and then bring it back up to the original circuit, calculating the voltages across and the currents through the individual pieces of the circuit. So I hope that helps you out a little bit with your understanding of resistors in series and in parallel. Thanks so much for watching. See you next time.